There is no reason for it. Yeah, I'll be asking that. Yeah. But anyways, yeah. In the case of row scaling, let's think about this matrix so that we multiply 2 on the first row. Then what will be the resulting determinant? Huh? Yeah, that times 2, right? So that was the very first properties that we start our determinant properties with, right? That was all the beginning of different all the various properties of determinant. Yeah, so yeah, it was just about the determinant, okay? And then using these determinants, again, these are also what you learned already. So if so we are talking about the invariable matrix theorem when your matrix is invariable, and then now we can utilize this eigenvalue, and then if your 0 is not the eigenvalue of your matrix A, and then it means your matrix is invariable, which means, so we consider this, right, A minus lambda I, it should be 0, right? And then so lambda is not eigenvalue, which means, yeah, that means when plugging lambda as 0, and this one will not become 0, right? Or this part will be removed after plugging lambda in with the 0, and then it means determinant of A will not be 0, and that is the same as this invariable matrix case, right? And then also the same thing is described by this determinant of A is not 0. Okay, then yeah, these are what we covered last time in the determinant part. And then now let's get into this characteristic polynomial. And so again, we want to obtain pairs of eigenvalue and eigenvector, right? And then last time I mentioned that first step is to find eigenvalue, right? And then in order to do that, we have to solve our characteristic polynomial, which means we have to set this equation, right? And then let's write this equation by using this example. So in general, the A minus lambda I will become like this, right? And then in general, it will be quite difficult, quite tedious process to compute the determinant of this 4x4 matrix, right? But fortunately, this is an upper triangular matrix, so as the student mentioned, in this special case, we can simply write this characteristic polynomial, which is this guy, as 5 minus lambda and 3 minus lambda and 5 minus lambda and 1 minus lambda equals 0, right? Because simply the determinant of this matrix will be the product of all these diagonal entries. Okay, then the root or the solution of this this equation can be easily obtained. Lambda can be 1, 3, and 5. Okay. And then for each value of these, we just plug them in, and then solve for its eigenvector, right? And for sure, if you use one of them as lambda, and then the resulting matrix of A minus lambda I, this guy will become singular matrix, which means you should be able to, you must find the linearly dependent columns all the time, because these values, these lambda values were obtained so that your matrix A minus lambda I to be singular, right? Because of this property. Okay, and then you can obtain some, let's see, you can obtain some non-trivial solution for this A minus lambda I for lambda being 1 or 3 and 5. Okay, and here your equation looks like this, and then since we have these 2 times, so I'm gonna just put the square sign here, and then this will be your characteristic equation. Okay, and then first of all, how many solutions? So how many solutions do you have in this equation? 4. Okay, so basically it's a fourth order polynomial, right? Which is the same as the matrix size. If the matrix was 4 by 4, and then you will always obtain fourth order polynomial as your characteristic equation or polynomial, right? And so in general, by considering the complex numbers, you will always have 4 solutions, right? I mean, counting the multiplicity. So the student answered the number of solution in this case as 4, which means even though we have 3 different values, this 5 is counted twice, right? Twice. Okay, and so let me introduce this kind of a now we have to think about this multiplicity very carefully. So it's a quite important concept. So the redundancy, I mean the count of the same solution, is called multiplicity, and especially in this case, it is called algebraic multiplicity. Algebraic multiplicity. I mean, algebraic means almost nothing. I mean, just multiplicity. Algebraic multiplicity is the same as the multiplicity that you already know. Okay, and multiplicity is what? What is it called in Korean? Multiplicity. 무슨 근이라고 하죠 이걸? 중근이라고 그러죠? 그래서 이거는 중근, 그다음에 여기가 만약에 3이었다. 그럼 이거는 뭐 3중근, 4중근 이렇게 얘기하죠. 그러면 중근은 2중근이라는 거고요. 그죠? 2중근에 그냥 2자를 생략한 거고. 그래서 중근, 중이 뭐냐? 중복되다 할 때 중이고요. 몇 번 중복되느냐? 그 몇 번, 그 카운트, 그게 여기서 멀티플리시티라는 거예요. So basically this number is a multiplicity for this for this solution. Okay, and counting these multiplicities, the total number of solution is again 4. Okay, and then let me also tell you another interesting property. So for each of these solutions, let's now think about the number of eigenvectors corresponding to each particular eigenvalue. So for these 1, it will at least have one eigenvector, one non-trivial solution, right? Because the definition of this solution or this characteristic equation is defined that way, right? And so 1, 3, and 5 each will have at least one eigenvector. Okay, so again, we now think about the count or the number of eigenvectors for each particular eigenvalue. Okay, and so at least each of these eigenvalues will have at least one eigenvector. And also we discussed about the eigenspace, or the dimension of the null space of your A minus lambda I. Okay, so I'm just copying our matrix, and I'll just put some random number. Okay, so in this case, so this guy has the same characteristic polynomial. Then let's use lambda as maybe 3. And so 5, 3, 5, 1. And what would be A minus lambda I? It's 2 and is 0 and 1. 2 minus 2, right? Okay, then so this will be our new A minus lambda I, and then we have to find the solution X. So it is just the null space, right, of this new matrix after subtracting lambda I from A, right? And then what is the dimension of the null space in this particular case? What is the dimension? Huh? The dimension of the null space means dimension of the null space, which means, so imagine you factored it as some parametric vector form. So we have some free variable and possibly another free variable, and then you will have some vector, right? And then in that case, we have 2 dimensions for our null space, right? And those vector, number of those vector was the same as the number of free variable, right? Just a free variable. And then in this case, how many free variables do we have? How many free variables do we have? So first of all, is it echelon form? No, right? So we have to cancel this out, right? And we can easily do that, right? And then, let's see. Then we also have to cancel this out. And so the free variable is the second one, which is the number of free variable is just 1, right? So in this situation, you have one dimensional null space, or especially that was called eigenspace for this eigenvalue, right? Eigenspace is basically the null space of A minus lambda I for particular lambda. So that had the special name of eigenspace, and then the dimension of the eigenspace is just 1, right? Okay, so this had a the dimension of the eigenspace, or simply we just consider that as the number of eigenvectors, okay? And this guy had 1, and this guy will also have at least 1, and this guy will also have at least 1. And will it be possible that we have two-dimensional eigenspace? Two-dimensional eigenspace. Two-dimensional eigenspace. Okay, so it is definitely possible that we have a two-dimensional eigenspace. Let me give you the example. So instead of 5, 3, 5, 1, let's slightly change our matrix so that 5, 5, 3, 1. In that case, our our characteristic polynomial will remain the same, right? It will be just simply simply be the product of diagonal entries, right? I mean minus lambda version, right? Okay, so in this case, so I slightly changed it so that these two entries became switched between them, and then let's now consider lambda as 5, and let's in the similar manner, let's consider our diagonal entries. So 0 and 0, and what about this guy? It's minus 2, right? And minus 4, right? So in this case, how many eigen vectors are there, or how many free variables are there? Huh? Is it an echelon form or not? Yeah. So that's a good question. So so we are starting here, right? So still the first column is okay, and we step up just one step at most, and then we can have this kind of form, and thus we will have a 3 pivot variable, or 3 pivots and 1 free variable. Okay, so this one will still have a 1 eigen vector, or 1 dimension. Dimension is 1 for our eigenspace, but yeah, so I shouldn't have switched them. So let's see. So let's get back to this example, 5, 3, 5, 1. Then in this case, 0 and minus 2, and 0 and minus 2, minus 4, right? Okay, in this case, let's imagine the staircase form or echelon form, and then we will have here, right? Then okay, I have to change one number again. I want to have this value be cancelled as well. Okay, so in this case, if you imagine like a row reduction, and then we will just multiply it by 2 and then subtract it to the second row, and then the equation will be the echelon form will be like this, right? So we can have this guy as pivot, and then we can cancel these out, right? Okay, so in this case we will have 2 free variables, right? So that's definitely possible for some matrix, and so you now have a 2-dimensional eigenspace. Okay. Okay, so so in this manner we can think about the number of eigenvectors for a particular eigenvalues, and that number of eigenvector is corresponding to the dimension of eigenspace. But here, let me tell you one interesting property. So previously we considered the algebraic multiplicity, right? The count of the same solution, right? And that number will be your maximum number of free variable, or the maximum number of dimension for eigenspace. So in this case, we have single count, or this will have a algebraic multiplicity as 1 because it's just a single solution. And this guy has the algebraic multiplicity as 2, because simply we see the solution as 5 twice, right? And then this one will have multiplicity as 1. Okay, so these three solutions will have the so let me rewrite it here. 1, 3, 5. These are our lambdas. So let's create some table. And the next row is algebraic multiplicity. Oops. Okay, so I'm creating this table on the bottom right, and so I just listed up three different solutions, and algebraic multiplicity will be, this algebraic multiplicity should be at least 1, because at least we should be able to find at least one eigen vector for this eigen space, or the null space of A minus lambda I. But those the algebraic multiplicity can be simply counted by this. So lambda being 1 has the multiplicity as 1, and 3 as 1, and 5 as 2, right? And then now we consider another version of the multiplicity, but that multiplicity, the second multiplicity, is called geometric multiplicity, and this is the same as the dimension of null space of A minus lambda I for these particular lambda values. Okay, and those values, okay, so we have three values, and these three values will be at least 1 or greater than 1. Okay, but its maximum value is bound by these algebraic multiplicity. So that is the property, which is really important property, but I will not prove this. Okay, so let's just understand, or just take it as a granted. So these values, what will be these the first value, the first question mark? So it should be at least 1, but the maximum value is bound by 1, because it is just to have 1 as algebraic multiplicity. So this first number will be 1, right? And then likewise, the second number will be 1. Then what about the third number? This guy can be 1 or 2, right? Because it's at least 1, equal to or greater than 1, but also it should be less than or equal to 2. Okay, so that is the main property of this, in terms of the relation between geometric multiplicity and algebraic multiplicity. So this is quite an important part, and then we will utilize that fact in the next chapter, which is about the eigen decomposition. But anyways, so let's try to understand this a little bit more intuitively in terms of the number of free variables. So initially, the solution of 5 had a 2 as algebraic multiplicity, and it means when solving this kind of equation, A minus lambda I or 5i times x equals 0. So this guy will have at least one free variable, but at the same time, it will have at most 2 free variables. So it is never possible that this equation has 3 free variables, because lambda being 5 had the algebraic multiplicity as 2. Okay, so that is a little bit more practical meaning. Okay. Okay, so this is actually the part of the very last part in the next chapter, which is the last chapter of eigenvalue and eigenvector. But so yeah, we will come back to this and utilize this shortly in the next chapter, probably later today. Okay, so let's keep that in mind for now, and then move on to the next notion called similarity. Okay, so this one is practically really important, but this one is a little bit separated from what we will learn. But yeah, this is an important concept, so let's study it anyways. Okay, so we now learn about the formal definition of being similar between the two matrices. Okay, so you have a matrix A and you have another matrix B, and someone said, okay, these two matrices A and B are similar. And what does that mean? Okay, what does that mean? It has a formal definition. Okay, formal definition. Similar is not a vague statement. Okay, so it looks quite similar matrices, like for example 1, 2, 3, 4, and 1, 3, 2, 4. Okay, these two matrices are similar, but it's not like that. It cannot be said that way. Okay, it has a particular formal mathematical definition, and that definition is this. So when these two matrices are similar, this is when those two matrices A and B are satisfying this kind of equation. So if you can find some matrix P and you multiply it on the right of the matrix A and then its inverse on the left, okay, so it's like something like this. So okay, let's think about a very special case. A and B are scalar values. R3 and A, which is A and B. 3 and 8, are they similar? Why don't you think so? They are not equal, but we have to think a little bit more in order to determine whether they are similar or not. So if we can find some P, okay, multiplied on the right and its inverse on the left, okay, if we can find such kind of P, and then 3 and 8 are similar because of this definition. Can we find P? Can anyone give any possible value for P satisfies this? So first of all, P is just a scalar, okay? P is just a scalar. And what would be the value satisfying this? So let's 8. Will there be any other value? 8 or 3? 3? Okay, so you guys are thinking too hard. It can be basically any values except for 0. Because, so let's just use a simple case of 1. And what is 1 inverse? It's 1. So 1 times 3 times 1. Ooh. Ah. Yeah, sorry, I was wrong. Yeah, I was wrong. Yeah. So 3 and 8 are not similar. Okay. So in this case, it should be the same value, right? So it would be the same value are similar. Yeah. So I was confused. I'm sorry about that. Yeah, but anyways, you guys know, you guys get the sense about how it works. So you basically multiply some value or some matrix, and also in order to cancel that out. But now you are canceling this by multiplying its inverse, but on the left, okay? And in that case, these resulting matrix B and the original matrix A are said to be similar, okay? So in that case, we call them matrix A and B as similar matrices. Okay, and this guy can be written as just multiplying P and P inverse on the left and the right, and we will have like this P times P inverse. So in this manner, okay. So in practice, it doesn't matter whether you put the original matrix on the right and the inverse on the left, or you switch between the original matrix and its inverse, right? It doesn't actually matter, because in this case, if you call this P inverse as Q, and then it will be the same as Q inverse B and Q, right? So you found some matrix Q, right, that satisfies this original definition of similar matrices. Okay. Okay, and then from the function, from the perspective of a function or the transformation, we can think about this similarity transformation, so that you have a matrix A here, original matrix here, and then you now carefully choose your matrix P. Okay, and then you multiply P inverse A and P together, and then the resulting matrix, let's call them as B, and then of course A and B are similar. Okay, similar. But if this matrix B is some special matrix, and then that's when this similarity transformation becomes meaningful. Okay, it's meaningful. So you can find your matrix P, carefully find this matrix P, so that the resulting matrix B as some meaningful or special type of matrix. Okay, so that is kind of a peak of the next chapter, and we are currently studying eigenvalue and eigenvector. And so this matrix P, this matrix B, the resulting matrix, so you want to find some matrix P, so that this matrix B as diagonal matrix. Okay. And these diagonal matrices will be your eigenvalues. So in the case of a previous example, so we had 1, 5, and 3. And so you want to change your original matrix A into some diagonal matrix that have like this kind of diagonal entries, and the diagonal matrix, and then in that case your matrix P, such that this A becomes B after this transformation. Okay, so P will be your eigenvectors. Okay, eigenvectors. So that will be the main part that we will learn probably today. Okay, I will just explain it shortly, but before then, let's just finish up this chapter. Okay, and so this similarity transformation, or if matrix A and B are similar, and then between A and B, they have some special properties, and that property is this guy. They should have the same characteristic polynomial, and thus they will share the exact same set of eigenvalues. Okay, is an exact same set of eigenvalues. Okay, and then let me point out one thing that I missed in the previous slide. So when talking about the similarity, similar matrices, when saying matrix A and B are similar, and then both A and B should have the same size of matrix. So they should be the same size of matrix, and also they should be the square matrix. So both of them are square and the same size of matrix. Okay, so that's the only situation we can decide or talk about whether they are similar or not. Okay, then this theorem says if A and B are similar, and then they have the same characteristic polynomial. And then let's look at the proof briefly. So if A and B are similar, this is their relationship for some P, right? And then now, if we consider the characteristic polynomial of each of A and B, and the characteristic polynomial of A will be something like this, and also for B, we will have this. And this theorem 4 says those two equations are exactly the same. Okay, so let's see. Let's prove this guy. Okay, so from B here, and let's start with here, which is this part. Okay, and that part will be, so B is the same as this, and lambda I, we do one trick of changing identity matrix as P inverse P, and you can factor these P inverse out. Okay, so this part is the same as we have this situation where we have lambda here and we have P inverse and P, right? So far so good, right? And then we can change the order between lambda and P inverse, right? Because lambda is just a scalar. Okay, and then it can be P inverse lambda and P, and we can factor these P inverse, and here we have a P inverse here, and so we can factor this P inverse out, and the remaining part will be A P minus lambda P, and then we can further factor these P out on the right, and P inverse and P, and then these part will be A minus lambda, right? And then let's think about the determinant of this whole part, and then it will be the same as determinant of this part, right? And then the determinant will be decomposed into the product of each matrices, and this part will be cancelled out, right? Because the determinant of P was 3, and then this guy, the inverse matrix and its determinant will be 1 over 3, right? And this guy will be the same as this guy. So we proved that the characteristic polynomial of matrix A and B, which are similar matrices, they will have the same characteristic polynomial. Okay, so what does that mean? So let's look at the meaning of it. By using one example. So there are some warnings in this slide, and that warning is saying that these two matrices are not similar. Okay, so in this case, what is the characteristic polynomial? 2 minus lambda and 2 minus lambda and 2 minus lambda squared equals 0. So this is characteristic polynomial. And what about this? 4 minus lambda and 2 minus lambda equals 0, right? This is, so in these two cases, the characteristic polynomial itself is 2 minus 3 lambda plus lambda squared. These two equations are certainly different, right? Certainly different. And so they are not similar matrices. Okay. They are not similar matrices. But what about these? What about these? So in this case, they will have the exact same characteristic polynomial, right? So in that case, yeah, they will be similar matrix, which means you you should be able to find some matrix P so that your matrix A times P and P inverse will be the same as 1. Okay? Okay, so again, this theorem is saying that if matrix A and B are similar, and then they will have the exact same form of characteristic polynomial. Okay? So that is the main point of this theorem. Okay, and then let me emphasize this part. And so, what is the meaning of the same characteristic polynomial? And obviously, it means those two matrices A and B have the same eigenvalues, right? The exact same set of eigenvalues, right? So that is when the characteristic polynomials are exactly the same.
They have the same mechanism, they will have the same division also.
Yeah. So when talking about the similar matrices, we assume that the matrices A and B are the same size and they are square matrices. Because if they are not square matrix, and then we cannot even compute or define the determinant of it. So we only define the determinant on the square matrix. Okay, so any questions so far? Okay, and then let's move on to the third chapter called the diagonalization. So diagonalization means you are given the matrix A, okay, and then you consider, let's see, you consider this kind of form, okay, or this guy is the same as, let's just multiply P inverse and P on the left and right respectively, and then it will be this, okay. So this is a really important equation. So let me tell you what we want to do by using this equation. So we are given this original matrix A, and then so you multiply some matrix P so that P inverse AP becomes another matrix D, which are similar matrix, but as I mentioned briefly in the previous chapter, we want to obtain the matrix D as diagonal matrix. Okay, so in that case, again, this is called similarity transformation, and you actually made your matrix A as diagonal matrix. So that's why we call that as diagonalization. Okay, so originally your matrix was not diagonal, but now you have diagonal matrix D after this similarity transformation. Okay, then now this theorem 5 is the main part of this chapter 5.3, and this is not so much about how to study how to prove this. So it's not so much about how to prove this, but more about the intuitive understanding about what it means. Okay, so let me just explain. Okay, so I'm gonna bring this guy. P inverse A P equals T. Okay, then I can rewrite it as this: AP equals PD, right? By just multiplying P inverse on P on the left. Okay. Okay, so let me tell you how we can construct this matrix P and D using eigenvalues and eigenvectors that we learned. So A is three by three matrix, and let's first obtain or compute eigenvalue and eigenvector, and we would compute the characteristic polynomial of this and then set it as 0, right? And then suppose we obtained lambda as 1, 3, 5, and the eigenvector for lambda as 1 as maybe 1, 1, minus 1, this guy as 1, 0, 1, and this guy as 1, 2, 3. This is just a random vector that I just gave you, but suppose these eigenvectors were obtained from each of our eigenvalues. Okay, and now for this first pair, I can write this guy as this form: ax equals lambda x. So each pair should satisfy this, and we have a matrix A here, and this vector x, 1, 1, minus 1, and 1, 1, 1, and what is the lambda? Is 1. It should be satisfied. And then the second one is A times 1, 0, 1, and 3 times 1, 0, 1. So that will be also true. And another one is, yeah, it's just tedious, but let's just write it one more time. 1, 2, 3. Okay, so now let me tell you how we can aggregate them into one single equation. One single equation. Let's first try to aggregate those two parts. Okay, so in this case, let's call this as V1 and lambda 1 V1, and this guy as V2 and lambda 2 and V2. Okay, then how about this? We multiply A on the left and we form some matrix. And this matrix is composed of V1 and V2. And this guy is the same as this guy, and this guy is the same as this guy. Okay, and what will be the resulting matrix representation. So in this case, so let's forget about the right part, but focus on this part. And in this part, it will be 8 times V1 and 8 times V2. And should it be plus or not? It shouldn't be plus, right? So that was one of the questions in the exam, right? So this doesn't make sense at all, right? So if you study the linear algebra and then yeah, it's really obviously wrong. Okay, and so after multiplying these two matrices, the first column will be 8 times V1, and then second column will be 8 times V2, right? Yeah, so far so good, right? And then each of the column will be represented as lambda V1 and lambda 1 V1 and lambda 2 V2, right? Because 8 times V1 in this first equation, 8 times V1 is the same as lambda 1 times V1, right? So we replace this guy by this lambda 1 times V1 and 8 times V2 from the second equation. 8 times V2 equals lambda 2 times V2. Okay. And so we are obtaining this equation. Okay, and then we can factor this out in an interesting manner of so we have the same vector v1 and v2. Okay, and then how can we factor those lambdas, lambda 1 and lambda 2, as its own matrix? So let's try to obtain this matrix, and this guy can be written as v1 times lambda 1, of course, plus 0 times v2, which is a linear combination of v1 and v2, right? And this is a special case of a linear combination, right? And so the first column, let's see. Okay, so we can represent this first column by the linear combination of those two columns, okay, by using the linear combination coefficient as 1, 0, not 1, 0, lambda 1 and 0, okay. So that way we obtain this linear combination coefficient, right? And then what about this part, lambda 2 times v2? So similarly, we can represent them as 0 times v1 plus lambda 2 times v2, right? And so the linear combination coefficient will be 0 and lambda 2, right? Okay, and now let's use the last one as well. Okay, last one as well, and we start with the matrix A here, and on the right we just align our eigenvectors v1, v2, v3. Okay, and then it will be the same as v1. It will be the same as V1, V2, V3, and times what? Yeah. Lambda 1, lambda 2, lambda 3. And these diagonal matrix. Okay, diagonal matrix. Okay, so now, now let's call this matrix as P. Okay, and we have P here again, right? And this one will be our D, which we can find here. Okay, and so for P, we just align column by column, right, of our eigenvectors. And for this, and then if we think about this similarity transformation, where we use P as this matrix, and if we think about this inverse matrix, which is the inverse matrix of this matrix that has the eigenvector as its column. Okay, so this is our P, and if we can consider, if we can think about P inverse, and P inverse times A P will become your diagonal matrix D, and this D will have the diagonal entry as eigenvalues. Okay, so that way this guy, which is this guy, is viewed as the similarity transformation, okay, of making your matrix A into the diagonal matrix D. Okay. So altogether, I'll just rewrite this P inverse A times P as D as P and D and P inverse. Okay. So in this case, again, this P will be this matrix. Its columns will be the eigenvectors. And what is the D? What is the matrix D? It will be the collection of eigenvalues on the diagonal entry of this matrix. Okay, and this is called eigendecomposition. Okay, and then from another view, if we view this guy as this, and then by using some similarity transformation, we made matrix A into the diagonal matrix, right? So that is called a diagonalization. Okay. Okay. And here, let me emphasize one really important part, and that important part is this guy. This part. So here, we assume that the matrix P is invariable, right? The matrix P is invariable. So it means P should be the square matrix, right? At least it should be the square matrix. And it means in the case of 3 by 3 matrix, you should be able to, you must find 3 eigenvectors, right? But what if you find less than 3 eigenvectors? And so in this particular case, so we studied about this algebraic multiplicity and geometric multiplicity. So in this case, the matrix was 4 by 4 case. And so, when thinking about the similarity transformation, the P matrix should be 4 by 4 matrix. It should be the same size. So that's when we can multiply it on both on the right and the left, right? And so you have to, in order to perform the similarity transformation, you have to find invariable P, okay? But your matrix P is determined, or P is made, or P is formed by using eigenvectors as the column of its matrix, right? And that means you have to find 4 linearly independent eigenvector. Okay, so that's when you can obtain this eigendecomposition and also this diagonalization. So when will your matrix A have less than 4 eigenvectors? That's related to this geometric and algebraic multiplicity. So altogether, what is the summation of these 3 numbers? It will be 4, right? And for each values, those geometric multiplicity, which are the number of eigenvectors, that is less than each of these numbers, but also at least is greater than or equal to 1, right? Of course. But in this case, it should have 1, 1, and it can be 1 or 2. But if it has just 1, okay. So in this case, you can find only 3 eigenvectors, right? And so that's when you cannot. So in that case, you cannot obtain this diagonalization or eigendecomposition. Okay. And also, let's suppose we obtained 2 eigenvectors here. So in total, we have 4 eigenvectors. So when forming our matrix P, by forming the columns of this matrix as these 4 eigenvectors, okay. So at least we have a square matrix because we now obtained 4 eigenvectors. But one important point is to think about is whether they are linearly independent or not. Are these 4 eigenvectors linearly independent or not? So if all of them are linearly independent, and that's when we can obtain P inverse, right? P inverse here. But what if our eigenvectors are linearly dependent between some vectors? Okay, in that case, we cannot obtain P, even though we obtained 4 eigenvectors. P will not be linearly independent. I mean, invariable, right? Okay, so time's up. So I continue the discussion about their linear independence, and that's about this theorem in the first chapter. Okay, this will tell you some aspects about this characteristic. So that's it for today. And please spend your time on your homework. Let's meet this Thursday.
출석 오늘 지금
What's the scope for the final exam?
The entire scope
Until what chapter?
until
Is it chapter 6?
and we will do a little bit more. So we are currently doing chapter 5, and we already covered chapter 6. Then we will cover chapter 7 or 9.
7 or 9?
Yeah, 7 or 9. So I plan to cover 2 more sub-chapters. So I'm not sure if it's 7 or 9, but it will be 7.1 and 7.2 or something like that.
Can I see the explanation?
About
Like I
Uh-huh.
didn't capture it. The one that you explain everything. I mean for last one. No, not this. Yeah. Can I take a picture?
sure, yeah. So I'm posting the lecture videos on the YouTube.
I know, but I'm confused sometimes with
Oh,
the
okay, I
videos.
see.
So,
Yeah, no problem.
I just need because I understand.
Yeah.
the students.
No problem. Yeah.
Yeah, Professor, I was when is the final exam? I'll be.
It will be. So the final exam will start on. The period will start on Thursday,
15.
right? And let's see.
Yeah, Thursday, right?
Yeah, Thursday. So
15 or 16, I don't know. 15 maybe.
yeah, right. So this one will be the first exam date.
Mm.
So I'll probably do the poll on whether we have an exam on this date or 20th. So it will be either 15th or 20th.
Can we make it 15?
15? Okay. Yeah, let's collect the
Yes.
the preferences.
Because I want to spend Ramadan in Saudi Arabia.
Oh, so you go back to your home country?
It's this last Ramadan. You know Ramadan?
Ramadan?
Ramadan.
Ramadan?
It's like 1 month we are fasting.
Yeah,
So
yeah,
it
yeah.
will be the last month I think that I will spend with my family for 5 years. At least it's 4.
Okay, thank you.